Okay, so we are going to be talking about magnetic circuit analysis today. And hopefully on Thursday as well. So the reason why I'm going to hit magnetic circuit analysis again is because I want to give you guys some more background on magnetic fields because I think it'll be necessary for you guys to understand how to design and analyze some of the electromechanical conversion devices that we're going to be looking at, like transformers, generators, and electric motors and all of that kind of good stuff. So before we get strictly into the magnetic circuit analysis portion, I want to do a very brief review of magnetic fields. Or actually, I'm honestly not even sure if it's a review for you guys. So we shall see. And if something seems weird or fishy, please stop me. All right. So magnetic fields are generated by electrical currents. And their behavior is governed by two equations. Okay. So our first equation is this guy. We have the closed line integral of the magnetic field vector H dotted into some differential line element dl. And this will be equal to a surface integral of the current density vector dotted into a differential area element. And this is called Ampere's circuital law. And we're going to call this guy equation 1. And I'm going to talk you through the calculus and all of that kind of stuff. We're not actually going to use this form pretty much ever. Where in this particular equation, H is the magnetic field strength or intensity vector, meaning the direction is important, and it has units of amps per meter. And then J is the current density vector measured in amps per meter squared. Okay. Our second equation is this guy. We have a closed surface integral of B, our magnetic flux density vector, dotted into some differential line element dA. And this is equal to 0. This equation is known as Gauss's law for magnetism. And this is going to be equation 2. The quantity B, right stylus. As I mentioned a moment ago, is the magnetic flux density vector, where magnetic flux density is measured in Tesla. And I want to put a note here because I'm not sure how familiar you all are with the unit of Tesla, but 1 Tesla is equal to 1 Weber per meter squared, or 1 joule per amp meter squared. So that when we mess around with units, we'll know what the hell's going on. Okay. All right. So we are going to figure out what exactly these mathematical statements mean and how to apply them. Okay. So our first equation, Ampere's circuital law, states that the line integral, let me write this down actually. Equation 1 states that the line integral of the magnetic field H around a closed contour C is equal to the total current passing through any surface S that is bounded by the contour C. And equation 2 states that the total magnetic flux density entering or leaving a closed surface S is equal to 0, or more simply, all magnetic flux that enters a volume must leave that volume. So written out, this probably doesn't make a whole hell of a lot more sense than the mathematical gibberish that I put up there either, okay? So what we're gonna do is we're gonna look at a couple of different geometries of systems and see how we can apply these things to make these rules make some sense, all right? So the first system that we are going to look at is the magnetic field due to a current carrying wire. Okay. So let's say that we have a wire or a portion of a wire, as the case may be, that is a part of a larger circuit, where those ellipses means this is connected to something else. Okay. And our wire carries some constant current I in this direction. And I'm going to assign a coordinate system for this. Okay. So let's call the horizontal axis the z-axis and the vertical axis the rho axis, and we're going to be working in a cylindrical coordinate system that's tilted over on its side effectively. That's not going to be particularly important, but we're going to exploit symmetry and things like that. Okay. So since this system has cylindrical symmetry, because our wire is just a long cylinder, we are going to choose a contour that is uniformly distant from the wire. So effectively, I'm going to say arbitrarily that the contour from my line integral is going to be this loop. So this is my contour C. I have chosen it such that it is a uniform distance away from the center of the wire. So all of these green lines have some length R. And since this has something to do with the surface that's bounded by contour C, I'm going to say that the surface area of this loop is our surface S. Okay. So what is the total length of our contour here? Or what's the length or circumference of that circle? What's the circumference of any circle? 2 pi r, absolutely right, okay? So the length of our contour is 2 pi r. What is the total current that's enclosed by our contour? So how much current flows through the contour? Just I, right? So that fancy pants line integral that I gave you guys a moment ago, H dot dl is equal to J dot dA for this particular geometry simplifies to H times 2 pi r is equal to I. And from that, we can see that H, the magnetic field strength, is simply equal to I over 2 pi times the radius. Or we could call this I over L, the length of the contour. Okay. So we have just applied Ampere's circuital law. Okay. What we have found out is that a current carrying wire generates a magnetic field H whose strength depends on the distance that we are from the wire. Okay. Perhaps some of you have noticed that when I solved for H here, I threw away the little hat on top of it, or the arrow on top of it that designated that it was a vector. So effectively, I threw away the direction. Okay. The reason why I threw away the direction is because to find the direction using math requires calculus that I'm honestly not sure that you guys know how to do. But you can absolutely find the direction of the magnetic field vector by using a simple tool called the right-hand rule. Okay. So the right-hand rule works like this. You take your right hand, you put your thumb in the direction of the magnetic field, and then your fingers curl around in the direction, or excuse me, your thumb is in the direction of the current and your fingers curl around to give you the direction of the magnetic field. So for this system, sorry, I scrolled slightly too far, where we have a wire in the horizontal plane carrying a current I, we could say that our magnetic field vector H comes out of the page at all points above the wire and is directed into the page at all points below the wire. If we look at our system where the wire is pointed towards us out of the page, our magnetic field vector circles around the wire like so, and it'll have this counterclockwise direction. If we looked at our current carrying wire as if we were at some point behind it and the current was flowing into the page, we'd still see a circular loop, but now our direction would be in the opposite direction, right? When we put our thumb into the page, it curls around in a clockwise fashion. So for the system that we have here and the coordinate system that I've defined, we would say that H is I over 2 pi r, and this is going to be in the theta direction, where A sub theta is just a unit vector in the theta direction. Okay. All right. How do we apply Gauss's law to this system? Well, Gauss's law says that any flux that enters a volume must exit the volume. So we've actually already applied it because our magnetic field lines have formed closed loops, right? Where, just to be clear here, all of this stuff in light blue is our H field. All right, so that's what happens when we apply Ampere's law and Gauss's law of magnetism to a simple current carrying wire. Let's get a little bit more difficult in our geometry and look at our second case. The magnetic field due to a solenoidal coil. So I'm going to attempt to draw a solenoidal coil here. So to help me out, I'm going to draw a cylindrical tube. So, yes, ma'am. So that's a fantastic question. B and H are both often called the magnetic field, and they're used largely interchangeably, and we'll talk about why that is in a little bit. I am going to try to make a distinction between the two quantities. So H is what I'm going to call the magnetic field or the magnetic field strength or the magnetic field intensity. And B is what I'm going to call the magnetic flux density. And the difference between those two quantities, to me, as a jackass with a PhD who happens to have a master's degree in physics, is that B fields have to do with materials and H fields don't. So if we're not considering what's going on with a particular material, I'm going to deal with H fields. If we do care about what's going on in the material, we're going to use B fields. And in just a couple of minutes, I'm going to relate those two quantities. But as far as the nomenclature goes, I'm going to use H when I'm talking about magnetic field and B when I'm talking about flux density. But largely those two things are practically the same quantity. They just have different units. So.
I just have to put it up.
No, no problem. All right, so let's see. I'm going to draw a solenoid. So here's my terminal for my wire, and I'm just going to wrap it around this cylindrical form. Numerous times like so. And let's say that my current I is flowing in at this terminal and flowing out at this terminal. I'm going to give myself here an axis of symmetry, just for the sake of argument, and so that we can say that this solenoidal coil has a radius of r, and establishing my coordinate system. This is the Z direction. And this is the radial row direction. Okay. So what we're going to do here is we're going to apply a similar process. We're going to choose a contour and then work with what that contour gives us. Okay. So I am going to choose another contour here specifically to exploit the symmetry of this system. And so I'm going to choose a contour where one vertical leg is along the axis of symmetry of my coil. Then I have my horizontal legs going out through the surface. And then my other vertical leg is a really long way away. Let's call this A, B, C, and D. Okay. So if we kind of zoomed in on my contour, we'd see something like this. We have multiple iterations of the wire carrying current I, and it's carrying that current into the board because the wire is wrapped around the outside of the that cylindrical form, right? So as it's wrapped around, the current is pointing in that direction, or when I put my hand like this, it's pointing into the board. So that's why I've drawn all of those currents directed into the board, okay? So what is the total amount of current that is enclosed by my contour? It's going to be N, the number of turns or the number of loops my coil has, times I, the current carried by the wire, right? So my enclosed current, I enclosed, is just going to be N times I, all right? Now, we don't know anything about the magnitude of the magnetic field yet, but what direction do you guys think it's going to have? So if we use the right-hand rule with our thumb pointed into the board, to the right, we can see that it's going to be pointed down, right? So pointed down. And to the left of the wires, it's going to curl and point up. Every one of those portions of wire is going to contribute something in the up direction, inside the coil, and something down outside the coil. So we should have some field up inside the coil and some field down outside the coil. And we determine those directions purely by using the right-hand rule, okay? All right, so now let's do some dumb, terrible math, all right? So our line integral, H dot DL, is going to be equal to the integral of H dot DL from the path A to B plus the integral of H dot DL down the path from B to C plus the integral of H dot DL along the path from C to D plus the integral of H dot DL along the path from D back to A. And since we're back to the point we started from, our line integral is closed and we're done adding terms to it. And this sum of integrals is going to be equal to our enclosed current, which is n times I. Okay. So how many of you guys know what the dot product operation is? You guys said that you've had applied calculus. Did you do any kind of vector calculus or anything like that? Okay. Fair enough. All right. So how the dot product works is effectively, if you have two vectors that are in the same direction, the dot product says that if they're in the same direction, they multiply. If they're perpendicular, the product of them is 0. And then if it's anything in between parallel and perpendicular, it's some other amount that's determined by cosine of the angle that's formed. Well, I chose a contour here specifically so that our magnetic field would always be either exactly in parallel with our contour or exactly perpendicular with our contour, so that we're always just going to get h times the length or 0. All right. So let's talk about the path from A to B. So the integral of h dot dl along the path A to B. So our path from A to B is in the up and down direction, right? And we have already established that our magnetic field is also in the up and down direction. So the line integral of h dot dl along the path from A to B is simply h times the length from A to B. Yay for easy calculus. For the part of the line integral from B to C, our magnetic field and our line are perpendicular to each other, right? Because our magnetic field is in the up and down direction and our line is in the horizontal direction. So those two things are 90 degrees apart. And so our line integral is equal to 0. We're going to see the exact same thing when we go from D to A. All right. So now we have that last bit, which is the integral from C to D. Of h dot dl. Okay. Now this is where the contour that I've chosen also has a special significance. Okay. I chose this contour, this path for my integration, such that that line element from C to D is a long way away from the coil. And the reason why I did that is because I know that the magnetic field intensity dies out the further away from the coil that I get. So if I choose my line element from C to D to be a long way away, I can just say that my H field out there a long distance away is probably 0. And so this thing is going to look like about 0, depending on how far away I am. So I'm playing with the calculus in order to get the result that I want, but we'll tie it back to something that'll make a little bit more sense here in a couple of minutes. So if I add all of these results together, what I find is that the line integral of h dot dl around my closed contour is simply h times L, the length of the solenoid, which depends on how long I choose to make my contour, right? So if I cover up some portion of the number of turns, it's got a particular length. If I do the whole length of the solenoid, it's got a different length, but it's just the length that I'm interested in. And this is equal to my total current enclosed by my contour, N times I. And from this, I can see that H is going to be Ni divided by L. And it'll have a direction in the Z axis. Okay. This is technically only true for 0 is less than rho is less than r, where r is the radius of my coil. So effectively, inside my coil, I have a fixed magnetic field intensity. Outside of my coil, we're calling it 0, but if I'm close to the coil, that's not going to be true. If I'm far away from the coil, it is going to be true, okay? So let's resolve a couple of things that I hand waved here, okay? By considering what happens if we put a material inside our coil, right? So I have this blue cylinder that I wrapped my wire around. What happens if that blue cylinder is actually made of something, okay? So in order to understand what's going to go on there, we need to talk briefly about magnetic materials. All right, so the structure inside the coil is what we're going to call the core, and the material that the core is made of can affect the behavior of the magnetic field depending on what type of material it is, okay? So there are more than this, but I'm just going to start with 3 simple types of material, all right? We have diamagnetic materials. A diamagnetic material experiences weak magnetization, and we're going to talk about, excuse me, that term magnetization here in a couple of minutes. In the presence of an external magnetic field. So if we apply an magnetic field using an electromagnet or something like that, we experience weak magnetization. They produce a magnetic field opposite to, so opposite in direction to applied magnetic fields. And some examples of diamagnetic materials are copper, gold, silver, water, glass, and salt, okay? So that's one thing that I find incredibly interesting about the properties of magnetic materials is that they don't make nearly as much sense, at least to me, as like the electrical properties. You raising your hand? Yes. Sorry, I ran out of steam and forgot a word. Thank you. So what I mean by that is we would generally consider copper, gold, and silver to be very good electrical conductors. Water and glass would be very poor electrical conductors, and salt is somewhere in the middle, right? So we have lots of different types of electrical conductivities, which I'm more familiar with, but all of these exhibit diamagnetic properties, okay? Now let's look at our second class of material, which is going to be the paramagnetic materials. So paramagnetic materials experience slight magnetization in the presence of an external magnetic field they produce a field in the same direction as the applied magnetic field. And some examples are, find out where I am in my thing, tungsten, aluminum, and magnesium. And then lastly, we have, or the last thing that we're going to talk about today are our ferromagnetic materials. Where a ferromagnetic material experiences strong magnetization in the presence of an external magnetic field. They produce a large magnetic field in the same direction as an applied magnetic field. And some examples are iron, cobalt, and nickel, and most alloys made of those three metals. Sometimes silicon gets thrown in there as well. Okay. So all three of these different materials react differently to an externally applied magnetic field. And that reaction is what I'm calling the magnetization. Okay. There is a material property that quantifies the magnetization, and that is what's called the permeability. So the ease of magnetization, or how easily magnetic flux can be established in a material is known as its permeability, mu. Which is defined in the following relationship. So this is going to be equation number 3, and B, our magnetic flux density, will be equal to mu times H, our magnetic field strength. So this is the relationship between B, and H, okay? All right, so for a particular material, its permeability is identified relative to the permeability of free space or a vacuum. So mu can be broken into two constituent parts, mu r and mu naught, where mu r is the relative permeability, and it is a unitless quantity, okay? And it simply scales mu naught, where mu naught is the permeability of free space, which is equal to mu naught is equal to 4 pi times 10 to the minus 9 henries per centimeter. So depending on the material, excuse me, the value of mu can vary from some small fraction of mu naught to several thousands of mu naught. So generally, for mu r less than 1, we have diamagnetic materials. For mu r is equal to 1, we have a vacuum. In truth, air is very, very close to this, like 1.001 times mu naught or something like that. So anytime we're in just regular air, we'll treat it like it's a vacuum. Relative permittivities that are greater than 1 are paramagnetic materials. And relative permittivities that are much greater than 1, we'll consider those to be ferromagnetic materials. So we're going to see that like paramagnetic materials have permittivities in the tens, and ferromagnetic materials have permittivities in the hundreds to thousands of mu naughts. Yes, sir. Four pi times 10 to the negative 9. That's correct. Where it's exactly 4 pi because this and the permittivity of materials was defined with respect to the speed of light in a vacuum. So this one gets a fancy number and the other one is a weird 8.854 times 10 to the minus 12, because that's how the math worked out. Yes. Yeah, so that means much greater than. Let me erase that second one so it looks a bit cleaner. So for most applications, or at least all the ones that we're going to deal with in this class, we want to produce the most amount of magnetic flux with the smallest amount of current, okay, because that's going to give us the most efficient transformation of electrical and mechanical energies, okay? So that means that we are going to want to utilize materials that have very, very high permeabilities, because a high permeability means it can generate a large amount of flux for a small H field, okay? So let's revisit our solenoidal coil, but look at what happens if we have a very high permeability core, okay? So this is just going to be a picture kind of explaining what's going on. So let me put my core material here. Gonna wrap my wire around it several times. Like so. So along the vertical axis, we should see that the symmetry of the system causes our mag just be in the up direction. We already established why that is using the right-hand rule. And inside the coil, we're going to have that same relationship. It's going to be vertical. But when we get close to the boundaries, we're going to see that magnetic field lines, and so our flux kind of leaks out. And because we know from Gauss's law that our field lines need to form closed loops, we're going to have something that looks like this. So effectively, inside of our coil, because we have a high permeability core material, we concentrate our magnetic field. And outside of our core, because we have air, our flux, our magnetic field lines spread out, okay? So mathematically, our B field, the magnetic flux density, can be defined as the magnetic flux, which is phi B, divided by A, which is the area of the surface that the flux passes through, okay? So inside of our coil, our magnetic flux density B is going to be equal to phi B, whatever flux we have, divided by the cross-sectional area of our core. So that's effectively this circle here. Maybe I should have used a different color than green so you can see it better, but it's just the circular cross-sectional area. And this is going to be simply mu times N times I over L. And I'm going to put approximately here because we have some leakage at the ends of our coil, right? So this is inside of our core. Outside, we're going to have our magnetic flux divided by the area outside of our core, okay? So the magnetic flux inside the core has to equal the magnetic flux outside of the core because they form closed loops. But what's the area outside of the core? Literally everything but the area inside of the core, an extremely large area. So we should see that our B field outside is approximately 0. So this relates back to the assumptions that we made about the behavior of the H field, okay? We do have magnetic field lines that leave out of the ends, but because we don't have anything forcing those lines to smush together, our flux outside, or our flux density outside, is very, very small, okay? Now, is there a shape that we can use that pretty much guarantees that we don't have any flux leakage? You guys, what was that? A circle, a toroid is the fancy physics name for it, a toroid. All right, so that's the last thing that we're going to talk about today, or before we actually get into magnetic circuits proper, which anyway. All right, so magnetic field. Let me see what convention I'm using here. So I did 1 and then B because I wasn't paying attention. So let's call this C. Magnetic field of a toroid, or toroidal coil. All right. So I'm going to attempt to draw a toroidal coil here. Please bear with me. I know this is going to look particularly shitty. I am largely incapable of drawing a nice looking circle. So here we have our toroid. Let's say, for the sake of argument, that the cross-sectional area A is circular. Our toroid has an inner radius of R1, an outer radius of R2. Now we're going to wrap a wire around this bad boy. Like so. And let's say that our current flows in at the top and flows out at the bottom. And once again, this is connected to some larger circuit so that we don't have current flowing through an open circuit, because as an electrical engineer, that will bother me. All right. So we can make a couple of observations based on what we have already learned today, or reviewed today, is what it sounds like. That's okay. Our magnetic field strength, H, inside of our core here should be effectively constant. I'm saying that because when we had a solenoidal coil, we've mathematically determined that our field strength was effectively constant inside of the core. And so if we bend the core back in around itself, that should be okay. If you want to think about it, a solenoidal coil could be part of an infinitely large toroidal coil or something like that. So since our magnetic field strength H is effectively constant in the area inside the coil, we have to be a little bit careful about the contour that we choose in order to apply Ampere's law, okay? And so what I mean by that is, if we choose a contour that's just on the inside of the coil, it will have a smaller length than a contour that we choose right before we get to the outside of the coil, okay? And those will technically give us two different numbers for our H field intensity. So what we're going to do is we're going to split the difference. We're going to take an average distance for our contour that will be halfway between R1 and R2. So here is our contour. And the distance out to this contour, we are going to call R, where R is the average value of R1 and R2. Right. So if there are n turns of wire wrapped around the core, we can apply Ampere's law and find that H dot DL will be equal to H times 2 pi R, which is equal to Ni, the current enclosed by our contour. And doing a little bit of math, we then get H is equal to Ni over 2 pi R in the theta direction in our coordinate system. And going a little bit further, we can call this Ni over L, also in the theta direction, where this L here represents the average length of the flux path. So in this structure, all of the magnetic field is confined to the region inside of the core. So from this observation, we can say that our magnetic flux density B is equal to mu times H by definition, or mu Ni over L in the theta direction. And our flux phi B is simply B divided by B multiplied. Right, stylus. Having technical difficulties here. Need to remember which random pocket in this bag I put my spare battery in. Or this little type stylus.
Yeah, 50%.
I think so. Let's see. Oh, I bought one of the damn things.
Yeah.
You come by my office, I'll give you one of mine in its package, or I'll pay you for it later. You spent money on it.
I got a package for them. They're hard to find.
They are. I found mine at a random gas station because I had to replace the battery before a class in like 30 minutes. So I couldn't wait on Amazon. So I just called every place I could think of.
Yeah, I did the same thing and that didn't work out. Even if they were
Yeah, it very much does. Thank you so much for being more prepared than I am, because I swear I had one of those in my bag earlier. All right. So our flux is simply the flux density times the cross-sectional area, which is going to be equal to Ni times A mu over L. Okay. So I wrote it in this funny looking form for a specific reason, okay? So Ni is the total current. So it is the quantity that actually produces the magnetic flux. Phi B is the flux that's traveling around inside of this thing. And so this looks kind of like Ohm's law or a variation of Ohm's law, right? So if we consider Ni to be a magnetomotive force, analogous to voltage in a circuit, and our flux as a quantity analogous to current that's flowing around the core, we can develop an Ohm's law relationship. So I is equal to V over R in an electric circuit will look like phi B is equal to Ni, our MMF, divided by a quantity, fancy looking R, I don't know what the symbol is actually called, which will be our reluctance, where, let's write that down. Reluctance measured in amp turns per Weber. And putting things together here, we can see that flux is equal to Ni over our reluctance, where our reluctance is the length the flux travels divided by the cross-sectional area times the permeability, okay? So now we've put all of the background information together to describe a magnetic circuit. Okay. So magnetic circuits are what's used when the geometry doesn't allow us to use Ampere's law. Okay. We can use the results that we've got from our toroid and apply it to any kind of weird or interesting shape that we care about, as long as we have a core material, excuse me, that has a very high permeability, because that's going to prevent any flux from leaking out of the system. All right. So let's consider the following system. Okay. I'm going to have a core. Like so. And this core will have some length in this direction. Let's call it L1. It will have some thickness in this direction. Let's call it T. It will have some length in this direction. Let's call that L2. It will have some width in this direction. Let's call that W. And then we are going to wrap our wire around our core. Some number of times. Like so. And there are N turns of our current carrying wire, current being carried, is I. Okay. So we can replace this rectangular structure, which if we tried to use calculus to analyze this would be an absolute nightmare because the symmetry doesn't work out well in a Cartesian coordinate system because of the way that magnetic fields curl around things. So the calculus-based way of doing this would just be completely and utterly awful. And instead, we can draw it as a circuit where our source is our magnetomotive force, Ni. And then each of the branches of this core structure are going to have some particular reluctance. So we could call this guy R left. I'm going to try to draw the fancy R's, but I apologize in advance if I accidentally draw a regular R because I'm drawing resistors. Here's R top. Here's R right. And here is our bottom. So, oh, and just to be on the safe side, let's define a couple of things here. So our flux is going to be traveling around the core in this direction. And our contour effectively that we're going to use for our average length will be this guy right here. I'm going to put arrows along this average length that is indicating the direction that the flux is traveling. All right, so if we wanted to find the H field of this structure, what would we need to do? Well, we know that for our toroidal structure, H dot dl just looked like H times L, the length, because all of our magnetic field was confined inside of our core. And this was equal to the MMF that was driving the flux around the circuit. So if we wanted to find H, this would simply be Ni, our magnetomotive force, divided by the average length the flux travels. So we scroll back up here. What's the average length the flux travels? So let's talk about the horizontal bit first, okay? Somebody spit something out. So it won't be L1. L1 minus W, right? L1 minus W because we have a length of L1 from here to here, and then we come back in half a W on each side. So L1 minus W, absolutely right. Okay. So this is going to look like Ni over 2 L1 minus W, because we have two horizontal sections. And then what's our what's the length that's traveled by the flux, or the average length traveled by the flux in the vertical directions? L2 minus W. There are two of those. So lumping things together, that's going to look like 2 L1 plus L2 minus 4 W. And if we had numbers for anything, that's what our magnetic field intensity would be, effectively at all points inside of our core. Okay. What if we wanted to know what our flux is? So flux, we found, was Ni over the equivalent reluctance of our core material, right? So in order to determine this quantity, we're going to need to figure out what the equivalent reluctance is. So our equivalent reluctance is going to be the reluctance of the left-hand portion plus the reluctance of the top plus the reluctance of the right-hand portion plus the reluctance of the bottom, where the reluctance of the left-hand portion will be exactly equal to the reluctance of the right-hand portion because they have the same length that the flux travels as well as the same cross-sectional area. So that's going to be, sorry, left and right, not left and top. My apologies. L2 minus W divided by mu. And then what's our cross-sectional area of this core going to be? So it's going to be this area here, right? Which is the width multiplied by the thickness. So W times T. And the reluctance of the top and bottom should be the same, where that's going to be L1 minus W over mu WT. Our equivalent reluctance will then be twice R left plus twice R top, which will come out to be twice L1 plus L2 minus, sorry, let me write that more clearly, minus 4W, all divided by mu WT. And from this, our flux, again, Ni over the equivalent reluctance becomes Ni mu WT divided by twice L1 plus L2 minus 4W. If we wanted to figure out our B field, that's just mu times H, which would give us mu Ni over twice L1 plus L2 minus 4W, or alternatively, our B field is defined as the magnetic flux divided by the cross-sectional area, which literally would give us the exact same result. And these are the different types of things that we could potentially hear about in this score. All right, so I have an example problem worked out here, but I have talked for 80 minutes straight. So I'm pretty sure you guys are sick of listening to me. I don't begrudge you it at all. I'm sick of talking. I'm happy to work the example problem if you guys would like me to. I also have an in-class assignment thing prepared for you guys to work on, which would be my preference, because then I can see what I managed to screw up and what you need further explanation on and all that kind of good stuff. So choose your own adventure. You work stuff or I work stuff. Can I work the example? Okay. No? All right. Sorry you got outvoted. I'll